Welcome to Oddly Real. I'm Nem Stefanovic. Hidden in plain sight is the underlying world of atoms. Every physical object is made of atoms, and that includes all living things as well. The properties that we measure in our everyday world, like temperature and pressure, or whether objects exist in a specific phase like solid, liquid, or gas, can all be explained with atomic theory. Even the reaction of chemicals all have an underlying basis at the atomic level. In fact, I'd go so far as to say that atomic theory is one of the most significant discoveries in the field of science. Although we might take it for granted today, the existence of atoms was debated for thousands of years before it was generally accepted in the last 200 years or so. Many times we're asked to learn about relationships like pressure is proportional to temperature when volume is held constant. But these explanations sometimes feel forced, like it's something that we're supposed to memorize. In fact, it's actually much more natural to think about these topics from an atomic perspective. In this episode, we'll look at how atoms behave and interact, as well as show how that relates back up to the world that we see in our everyday lives. Atoms are small, really, really small. They're roughly 1/10,000,000th of a meter. To visualize that, think about the size of an apple. If you enlarge the apple to be the same size as the Earth, then the atoms in the enlarged apple would be the size of the original apple. Atoms can bond with other atoms very strongly to form molecules. Atoms and molecules that are not bonded also like to stick together as well. That's why materials tend to stay together. A solid object or liquid in a container doesn't just fly apart, it stays put. If you look at molecules, they tend to exhibit an attraction to each other. The origins of these forces come from the electric fields in their atomic structures. The forces are attractive between atoms when they are at a little distance apart versus strongly repulsive when they are too close. There's an equilibrium spot in between that the atoms like to remain to keep balance and to keep the substance together. If you pull on an atom a little bit, there's an attraction to pull it back in place. And this force grows as you pull up to a point. If you pull even harder, the connection between the atoms is broken and they permanently separate. Alternatively, if you push hard on atoms to try to bring them closer, there is a very large repulsion. In fact, when you pull or push atoms close to their equilibrium point, they will restore themselves back into position when released. The amount of displacement from the equilibrium and the amount of restoration force to bring them back are proportional to each other. This is the basis for Hooke's law in a spring, but this only holds up to a point, since if you pull or push too hard, you'll deform the atomic structure of the material. Atoms are also in constant motion. They move, twist, and vibrate at all times. These different motions have energy, which is what we refer to as heat. The average energy of motion of the atoms in a substance are what we measure as temperature. For example, an increase in temperature means there is more atomic motion. If you add enough heat, atoms can move so much more that they pull away from the material and fly apart. For example, heat up water and the water molecules start to leave as steam. Let's put a gas inside a container with a piston on top. If we look at the molecules of a gas, they are separated from each other. They are in motion, colliding with each other, and they collide with the walls around them as well. A molecule that hits against the wall will produce a push. When lots of molecules are continuously hitting against the walls, there is an average push over those walls. That's what we call pressure. In this case, they'd also be hitting up against the piston on top. So we'd have to hold the piston down with some force to keep it closed. That force is the pressure times the area of the piston. Imagine if we increased the surface area of the piston, but kept the number of molecules per volume the same. This would result in an increase in the number of collisions against the piston. More collisions over a larger area means an overall increase in the force against the piston. Thus, force is proportional to the area where pressure is applied. Next, imagine if we double the number of molecules in the same space, thus doubling the density. Let the molecules have the same speed, meaning they have the same temperature. Doubling the molecules will mean that there will be roughly double the collisions against the container walls. So we see that pressure is proportional to density. Next, let's increase the temperature of the molecules without changing the density. This increases the speeds of motion in the atoms. The atoms will now hit the walls of the container harder, which increases the pressure. Hopefully, you see how thinking about materials at an atomic level gives a much more intuitive understanding of their properties without memorizing rules. Now try moving the piston down inward. The gas molecules will collide with the piston, and the piston will add some energy to the molecules as they bounce off, much the same way that ping pong balls will move away faster when hit by a paddle. The result is that the molecules will move faster, so the temperature goes up. When slowly compressing gases, they heat up. Conversely, slowly expanding gases will decrease their temperature. Let's look at an example of a liquid. When you decrease the temperature, the molecules will not move as quickly. Beyond a certain point, the molecules will start to lock and arrange themselves into a crystalline array. In most cases, this means the substance will decrease in volume, since it is more restricted in its structure. In a rare exception, water turning to ice actually increases in volume. This is because its crystalline structure arranges itself to have large holes in it. Note that even when substances solidify and the molecules lock in place, the molecules are still moving, they jiggle and vibrate. Melting a substance involves adding more heat to speed up these motions such that the movements can jiggle the molecules out of place to move more freely again. Thus, melting a substance collapses its crystalline structure. Interestingly, even at the absolute zero temperature, atoms don't completely stop vibrating. Nature demands that there's always a minimal amount of motion. It can't completely stop. In these extreme conditions, substances solidify, with the notable exception of helium. However, if you apply enough pressure to push the helium atoms together, they too can be solidified. The atomic theory also describes physical processes. For example, let's look at the surface of water with air above that contains water vapor, oxygen, and nitrogen molecules. The molecules in the liquid water are moving around. Once in a while, a molecule at the surface gets hit from another molecule, causing it to break away. This is evaporation. However, let's put a lid on the container. This will result in evaporated water molecules staying contained in the air above. Now, more water molecules from the air will collide back to the surface of the water and stay there. The human eye will not see these processes happening within a closed container of water, but the evaporation and rejoining of water vapor is continuously occurring in a highly dynamic atomic process. The rate of evaporation and the rate of rejoining is about the same, so the water level doesn't change with time. If you remove the lid again and blow away the moist air above the water surface, then more evaporation will take place, with fewer water molecules in the air above available to rejoin the surface. The water starts slowly evaporating away. When a water molecule gets knocked out of the liquid, it receives a bit more energy than average in the hit, taking that energy away with it as it leaves. That means the remaining water molecules have a little less energy overall. Thus, the liquid cools as it evaporates. When water molecules in the air collide back with the water surface, there's an attraction to the surface as it returns that introduces a little bit more heat to the liquid. Note that the oxygen and nitrogen molecules in the air can also enter the liquid and get mixed into the liquid water. Air is able to dissolve in water. Atoms and molecules are also able to exchange partners to form new molecules. When this happens, a chemical reaction has occurred. For example, carbon atoms attract oxygen much more than oxygen attracts oxygen or carbon attracts carbon. This is why when you burn carbon, carbon atoms will detach from their structure to join oxygen atoms to form carbon monoxide. This interaction of carbon joining an oxygen atom causes the pair of particles to snap together very strongly, which also causes energy to be distributed to its surrounding area. Lots of kinetic energy is released, energy of motion, which results in a lot of heat. Much of this heat produces hot gases, but it can also be large enough to produce visible light. That's what you see as the flame in the reaction. How about smells in the air? Smells also come from molecules that are randomly moving around in the air. Some of these molecules end up in our noses, which we can detect and process as a scent. But how far do molecules go in a gas before they collide with another molecule? There's a name for this, and it's called the mean free path, which is the average distance a molecule travels until a collision. This depends on the number of molecules present, but also on their size. For oxygen at room temperature and under normal atmospheric pressure, its mean path is about 6 millionths of a centimeter. Additionally, its average velocity is about 480 meters per second. That means oxygen molecules move over 50% faster than passenger jet planes. Finally, modern science has demonstrated the existence of atoms in many different ways. I want to describe one classic example that demonstrates an underlying atomic action. If you take a small suspension of particles and put it in water, then look at it using a microscope, you'll see a random looking jiggling effect. It looks like the suspension of particles is being pushed around in all kinds of different directions. This is due to atomic collisions between the suspension of particles with the particles of the water. We call this random jiggling Brownian motion. Thanks again for watching, and remember, oddly real, really interesting.